I'm going to talk about higher cyclic operads. First, I'll tell you maybe something about what cyclic operads are. We got a preview of this in Yuan's talk earlier this week. So an operad has a bunch of spaces. Pn with some insertion operations. And also write sigma n actions on each space Pn. Okay, so if I'm going to give you a cyclic operad, one thing I could do is say that, so I think about things in Pn as looking like trees, and the sigma n action permutes these leaves up here. So in a cyclic operad, I want to be able to extend this to a sigma n plus 1 action. Right, so a cyclic operad has an underlying operad plus or an extension of the sigma n action to a sigma n plus 1 action. So in particular, if I take this, just something that rotates, then it sends this to we now change the input, the first input, to be the output, and so we get a picture like this. Right, so this was 1, and this was n, and this was 0. Okay, so sort of a weird thing to do. And if you look at these pictures, you can sort of guess what how this operator should interact with the circ i's, and it's something like this. So I'm sticking G into position I. Well, in the new thing, now I've twisted the bottom thing. Right, so before I had like this is G and this is F. And now in the new thing, I move this by 1. So before I was plugging into the second spot, now I'm plugging into the first spot. Unless I go the other way, if I go all the way around, then I have to change this. If before I plugged it into the first spot, now when I do this, I'm going to have to plug into the last spot. And I'm also going to have to twist G. Yes. So something like this. Right, so we want to extend this action. Let's give some examples. More examples. We saw some a couple days ago. So the first one is the associative operad. If I think about this as a non-symmetric operad, I just have a point. There's only so many ways I can extend no action to a Cn plus 1 action. And then I want to bring that up. Okay. So as a non-symmetric operad, Sn is a point, and I want to have a Cn plus 1 action on it. There's only one way to do this. Send the point to itself. And we can actually extend this up to a full sigma n plus 1 action. Okay? Which will only be like the identity on the non-moving sigma element. Right. Another example is actually the, let's say, a variant of the framed little 2 disks. Maybe I shouldn't go too much into how you do it, but you have this outside disk, going out towards infinity. You think that is another disk that you can swap with the other guys. But work is required to show this. Okay. One example that we don't always have is the endomorphism operad. This is not always a guy because how would I extend the sigma n action on this thing to a sigma n plus 1 action? Right? If x is a space, I shouldn't be able to do that at all. It doesn't make any sense if you think about what's happening. You really need x to be some kind of self-dual object. Okay. So then this nth level is going to be, this is now the dual of x, so I can move that over by adjointness. Right. And then we can see where the sigma n plus 1 action should come from. Okay. So you need to make some assumption on x for that to make sense. So where did this come from? Well, these things come from Getzler-Kapranov. And they show that if you take an algebra over a cyclic operad, well, if A was just an algebra over some operad, I should be able to define some kind of operatic homology or cohomology, right? So a Hochschild thing. This lets me define a cyclic homology. Right, so some kind of cyclic P homology. Okay. And in the case of associative algebras, this gives you the normal cyclic homology. Okay. And I'm going to be talking quite a bit about colored operads. And these I just have, instead of all these circ i's floating around, I just have like partially defined ones. So what actually is this thing? So we start with a set of colors. And then for every list of colors, we have a space or a set P of P0 up to Pn. So you should be thinking about these as being when the color set is just a point, and then we have a list of n+1 things. You can see how to do a sigma n+1 action. This P0 acts as the output. Okay. So the way to draw this maybe is to think about an element here as a tree like this, where now I have P0 here, and here's P1, P2. Okay. And I didn't put any semicolons or anything between the letters because, remember, I'm allowed to rotate. So I can change that P0 to an input if I like by making P4 an output. Okay. So in this case, we have these partially defined compositions exactly. If the colors match up. Okay, so it's really inefficient to not wet the whole board. Is that correct? That's a bad idea. Okay. So we have operations like this. And if I'm going to do a circ I, that means I stick something into the ith of this. So this is assuming that Q0 is equal to Pi. I think the way Yuan drew it the other day, he was specifying circ ij's, but you can get at that if you include the rotating action. Okay, so just to write one thing about colored cyclic operads, you should think about, I said you have some kind of partially defined composition. If you look at a colored monoid, right, which, so this is some monoid where I have a partially defined composition. This is exactly the same thing as a category. Right, so these sets of colors should be thought of as the objects of my guy P. And so that's where this is coming from. Okay, so that's a little about colored cyclic operads and cyclic operads. I would like to present today let's say, a model for infinity versions of these things. Okay. And to do that, I'll introduce a category called the denjocyclic category. C. This is related to the Mordyke and Weiss dendroidal category, and I'll get to that relationship in just a minute. Okay? So here's what we have. The objects of this thing are going to be some kind of graphs. Well, what kind of graphs do I want to deal with? These should be graphs that have legs. Right, so not everything has a vertex. This is a perfectly good example. Maybe I'll even put this. Okay, so this is the kind of thing I have in mind, where you have at least one leg. And you are contractible. So I don't want any kind of cycles floating around there at all. And these are undirected. And I think for technical reasons, I actually want to keep track of ordering places. Right, so for every vertex in here, I have some neighborhood of edges that touch it. So I want to specify an isomorphism like this. So now I've given an order to it, and also for the whole graph. So this is my sample graph. this should have a bijection with some other set. Right, however many legs there are there. Maybe it would be better with a cyclic order, but I don't think it actually matters very much. Thank you, Marcy. I'll be sure to write your compliment down in my diary tonight. Okay, so this describes the objects of this category. What are the morphisms? Oh, let's give a couple examples of objects. That seems better. We have the graph with no vertices. Since we're contractible, it means we need a leg. The graph with a vertex and no legs doesn't fit into this because then we wouldn't have at least one leg. So this is an example. Okay. Other example, star n. This guy has one vertex and n legs. Okay, so this is star 6. And also Ln. These have all vertices are bivalent, and there are n of them. And since we're contractible, there's only one thing this could be, and it looks like this. So if I have a graph, I could talk about its subgraphs. And what this is, well, it's going to be sub-objects of the graph S, so that if ever I have a vertex, then I have all the edges adjacent to that vertex. Right, so the vertices of T should be contained in the vertices of S, and if V is in here, then the neighborhood of V, this is now some subset of edges in S. This is actually going to be in the edges of T. Right? So I know exactly what the neighborhoods of any vertex are. It's really just inheriting from the other one. So examples for this S. So this is a subgraph of that thing, right, without that vertex there. This is a subgraph, where now I've just taken that guy and the vertex next to it. This is a subgraph. right? All the ones that are just one vertex and then the thing around them is going to be a subgraph. Each edge is going to be a subgraph. Okay. What? Yes. So subgraphs should be in particular graphs. Maybe I don't care so much about that ordering. Maybe I do, but yes. They're the same kind of graphs. So now I'll use this to define the notion of morphism. A morphism R to S consists of two functions. One, it has a function which maps edges to edges. And two, it maps vertices of R I actually want to map into subgraphs of S. And I'm going to have to impose some conditions that these satisfy. But before I write down the conditions, let's draw a couple of examples, the sort of motivating examples for the rest. One thing I want to be able to do is if I have a graph that looks like this and has an edge, I want to be able to add a vertex in that. So think about this as representing an identity on a category or something. And which direction does this go? I guess it goes this way. Codegeneracies, they should go down in degree. Right? So I can throw away a bivalent vertex if I see one. That's the first type of thing I should have. And I'm actually going to say that that's the only time I can get rid of vertices. So if V is not bivalent, then so here, notice that if I'm doing this picture, I should be sending this edge and this edge both to that edge, and I should be sending this vertex to the subgraph that just has this vertex. Okay? And I'm leaving the rest of the graph alone for this picture. So phi 0 restricted to the neighborhood of V is injective. So those are the only kinds of edges I can collapse down, is when they're sitting at a bivalent vertex. And there are two more conditions. But let's draw the other examples first. Well, the other main example that I care about is this one. So this is called a codegeneracy. And then we also have inner coface maps. And what that says is whenever I have two vertices that are connected by an edge, right, so maybe more stuff goes on out here, then we have a map from the thing where I've identified those two vertices. So every vertex I can pull apart like that if I want to. Okay. And what we should be thinking about this is there's supposed to be like an element of P here, supposed to be an element of P there. This is going to represent some kind of circ I. Okay. And the last one is outer cofaces. But now I've run out of board space, so maybe I should write the other two axioms first, since I have this down here. These are just well-behaving as things. If I take my vertex and send it to some subgraph, I want that subgraph to somehow be related to the edges at that vertex. And also, vertices should only be in the image of one of these guys. Okay, so let's draw the outer coface, which is arguably the least interesting of these three types of maps. So if I have a picture like this, where the graph continues out here, but I have a guy just sitting there, a vertex, I can delete that vertex. Okay. So what you should think for these is that all of these maps are just subgraph inclusions. Okay. Any questions so far? So here are some sample kind of morphisms. And you also have isomorphisms and things. Notice I didn't say anything about preserving these orderings that I put everywhere. Those are just something useful to have around when we're actually proving things. And you could use them for other things too. For example, the dendroidal category.
Bill, sorry, I do have a question. So you were saying that restrictions along this codegeneracy
Yeah, so you should think about going the other way.
Exactly.
So this would be a circ I.
What's the operation point of view on that?
There isn't. It's more like what's a good Matt? You're saying mapping from 0 into something. I don't know if that makes sense. Yeah, no, actually, yes, that's exactly right. It's projection down, right? So we're starting with something. We don't want to consider this anymore. We just project that one away. Okay. Yeah, that's why I say it's the least interesting. But we still have it around. Yeah. Yes. Yes. Yeah, I'll say a little more about that, but yes, these generate the whole category. Well, along with isomorphisms. So, given the setup we have here, we can define the dendroidal category as a subcategory of this thing. And how does this look? Well, the dendroidal category of Mordek and Weiss is supposed to have rooted trees as its guys. So if I'm giving you a tree R, I have a distinguished leg because I've numbered them, right? So I have a 0th leg. And also for each vertex, I have like a 0th vertex there. So to tell if this is actually coming from a rooted tree with this kind of structure, I should just be insisting that R0V is closer to R0 so this should be the thing that points down towards the root. Right. So if I look at any vertex, the thing that's closest to this root is the one I've labeled 0 already. And a map, if both of these are rooted trees, is ordered or oriented well, now I have to check the same kind of thing. Is it taking the root at each vertex to something that's really close to the rest?
Sorry, Phil, can you remind me if the neighborhood of a vertex consisted of a set of edges coming out of it?
Yes.
Or a set of roots? Okay.
Yeah, these are the set of edges that touch that vertex.
Then what's this distance thing? Sorry.
Yeah, so I didn't tell you what the distance is, but you could think that in one of these graphs I can draw paths between these things. It's the minimal, the length of the minimal path, right? So I can go from edge to edge, as long as they're connected at a vertex. And so that's what I mean by this. Or you could label each edge as length 1 and think of it about a normal. This should be less than or equal to. Right, so it plays well with respect to this structure. And of course, this is actually conditioned. This isn't going to work for all the maps, so this is a non-full subcategory of C. A couple examples of objects that satisfy this thing, that are rooted trees. So the three examples I wrote down earlier are actually all sitting inside of the dendroidal category as objects. But of course, with morphisms, it's something a little bit different. If I look at automorphisms there, those guys are all permutations of these n+1 legs, but they fix the 0 one. So this is just going to be sigma n. Right, I can only order the change the order of the positively indexed legs. Whereas if I look at it in the full category, I get sigma n+1. And similarly, I guess this is going to be the identity. Right, I can't do anything there, but if I go to the whole thing and look at this linear tree, I can like reverse everything. Thank you. Okay. Right. And I think I'll just write a formula here. So there is a close connection between C. So I know this is a non-full inclusion and so on and so forth. But we can get a lot of mileage out of like knowing things about omega. So if I take just an arbitrary SC graph, or graph. And I pick any leg that I like. Then I can get a new guy whose underlying graph looks the same, but this is now a rooted tree. So what I do is I rotate the orderings 0 through the number of vertices, the number of edges at each feet. I'll just write by rotating the orderings, and you can imagine that this would work, right? There's this Cn plus 1 action on 0 up through n. And moreover, there's a unique equivalence isomorphism between these two. That's the identity on edges. So they have the same underlying graph, but I've just messed with the orderings a little bit to turn it into a rooted tree. Of course, I have to choose a root in order to do that. So here's one thing that we have. I can, let's say I want to understand maps from R to S. And I pick a root for S. Then we get a map like this, going through these isomorphisms. So if I take any root for R, I can look at this. And I sum over all the roots. This is nearly an isomorphism. Constant maps are the guys that factor through just the single edge. Right? So the whole thing breaks down because if I look at that single edge, there's no automorphism or no non-trivial automorphism. So that's why I need to stay away from constant guys. But then using this tells me good things about automorphisms of graphs, for instance. Right? I can see it as just, the usual automorphisms that you would see in omega, but then a whole bunch of stuff just coming from changing what the rooting is. Okay. So I'd like to of end with a theorem, maybe a definition. So I've set this C up so that there's a functor going from C to the category of all cyclic operads. And what does this do? Well, given a graph, this will generate a cyclic operad with the set of edges as the set of colors. And the HOMs are generated by the vertices. But this is not full. Let's maybe give an example of this. So let's take L1. That looks like this. I'm supposed to have a generator in V sitting in, I didn't name my functor, so let's just write P of E1, E0, E1. Okay, associated to V. But now I have inside of P, I can do this. Right, I can look at tau V. Right, I know that I have something like that by doing a rotation. And what is this thing? This is just some garbage. So gone E1, E0, so this should be E1, E1. Right, this isn't anything nice. Now, what I could do is I can look at P to P, which on object sends does this. And takes the generating morphism P in P, will map to this element. Okay, this is a valid thing to write down. right? This is freely generated, so I just have to say what B goes. Okay. That's not a morphism that comes from C, right? Because essentially what we're doing is we're taking this and we're mapping it to this, but this is not a subgraph. But that's okay for the following reason. Despite having that, we still have this theorem. Let's call this funct or something. Let's call this C. I don't know if that's a particularly good name, but it's a functor. Despite this thing not being full, if I look at this, and this is going to take as an input something here. To pre-sheaves on C. So despite C not itself being full, this is full and faithful. So that's why I'm not particularly concerned about C not itself being full. So this is maybe a starting point. This gives an indication of, like, if you're happy with the picture for categories or operads, about the sorts of things that you could try now in order to define higher versions of these things. Okay, we want to weaken the condition that the image here satisfies. Okay. Thanks. Yeah, so what it's saying, they're not getting destroyed. They're still there, but there's what do I want to say? So what this is saying is that I can see all the maps if I pass to pre-sheaves. Right? So I know that, like, if I look at the image here, right, this is now a bunch of stuff. If I actually don't just look in C, but I look in pre-sheaves on C, I can see all those extra maps that I couldn't see before. Ah, yes. Yeah, let me get back to you on that.